faction.
Yes.
Let's go. Okay. Good evening. Thanks for coming. And today we have. I'm very pleased that we have Andrew Lawrence here to talk about how architects and engineers would work together. And I don't want to take over too much of your time, so I will hand that over. And after the talk, Andrew kindly offer you to ask as many questions as you can, but not for another 2 hours. All right? Okay. So Andrew will make a start.
Great, thanks. I think wood, I'll start on these because I think wood is this incredibly versatile material. If I stand in the middle, does that work? Feels really weird. So you can do anything from the sort of skeletal type structure of Metz on the left that we did with Sugar Ban, right the way through to the Smile that we've just done in London. Hopefully some of you saw this. Working in CLT. Brilliant. It's all right, I'm always late for things as well, so it's kind of fine. Brilliant. Okay, thanks. So yes, as you know, 15 years ago CLT was invented. So suddenly now a timber building becomes like a giant piece of flat pack furniture. Huge range of things that we can build in wood. It's a really, really versatile material. But for me, the great beauty of wood is that you can see exactly how the building has been made. So this is inside the Smile. And you can see that each one of those 12 CLT panels that we used, you can see how that panel is made up of lots of small bits of wood glued together. And if you look at Metz, you can see how the members have been connected together. So everything is really, really visible. That's the beauty of a timber structure. But of course, it also means that architects and engineers have got to work really closely together because all the engineering is completely exposed. And so this, as an example, this was an early meeting for the Endless Stair. You might have seen it 3 years ago. And you can see there the model's not yet in its final configuration. But these sorts of projects, I was asked the other day, at what stage of a project an engineer needs to get involved. I mean, if it's going to be a successful project, it's literally got to be from day one, and particularly if you're working in timber. Now, another thing with wood is you've got to work with the strength of the material, and you will know this already, but the wood is fibrous. The function of the trunk of a tree is to get water from the ground up to the leaves. So we have this simple engineering model of a tree trunk, which is this bundle of drinking straws, something which is 5 or 10 times stronger parallel to the straws, whether you squash it or stretch it. Compared to perpendicular to the fibres, you've got something that you can pull apart the straws really easily. So when we're working in wood, we need to remember it's a fibrous material. We need to use it in its strong sense. And of course, the other thing about wood is it's so easy to machine. If we cast concrete, you're lucky if you can get plus or minus 5 millimeters tolerance. With wood, we actually machine it. So we can machine it down to perhaps plus or minus 1 millimeter. But also, if we want to make really complex shapes, there is no material that's easier to work in than wood. If you ask what are the challenges, I mean, it's pretty obvious, isn't it? Wood actually grows in these really awkward shapes and sizes. And if you think about those trees, they're not cylinders. They are, they're actually conical. So if you want to use that wood efficiently, you have to really cut those trees into fairly short lengths, 4, 5, 6 meters, because they're conical, you're going to be cutting these tapering bits off the sides. You don't want too much wastage. So wood cut from the tree is limited to maybe maximum 6 meters long. So now that doesn't matter if we want to build a small medieval barn. But of course, if you want to build a larger structure, come 1850s, we're looking at building big railway station roofs. well, the fact that you've got these rather short bits of wood cut from a tree starts to be a bit limiting. This is rather nice. So does anyone recognise what I've got on the right there? I'm sure it's a building you've all been in. Say it again. It's not Temple Meads, but it's in London. It's one of the London railway stations. That piece, that cast iron casting is still there. So this is the roof of King's Cross Station. So originally you can see it had timber arches. This is 1850s, so glulam doesn't exist, but you can see what's been done. Basically, boards with staggered ends, and they were bolted together. So this was a bolt laminated timber arch. But I think you can imagine that that was incredibly labour-intensive to do that. So, you know, literally about 2 years after King's Cross Station, Paddington Station came along. And by then, you know, the idea of being able to roll wrought iron sections had just been invented. If you think this is only a year after the Great Exhibition. So overnight, wrought iron has become a cheaper way of spanning a big space compared to those sort of early bolt laminated timber arches. And it was going to be about 100 years before wood started to fight back. And it was really during the Second World War. So the Mosquito was completely made of wood. You can see the detail of the wing on the left. And what you're looking at is you can see a tiny glulam beam with sort of plywood skins. So, of course, if you were going to fly through the clouds, you needed waterproof glues. So that was what happened during the Second World War, development of waterproof glues. Up till then, wood had been glued, but it was all using fish glues, milk glues, casein as it's called, not very waterproof. But now waterproof glues, now we've got something which we can use safely structurally. Even if the structure gets a bit wet during construction, it's not going to fall apart. And so what that means is that we can take those fairly short bits of wood cut from a tree, 5 or 6 meters long, and we can put a finger joint at the ends, and we can make much longer lengths. And I think you can see that finger joint, a long length of glue loaded in shear, is going to be really strong. Obviously what you wouldn't do is you wouldn't just butt the ends of 2 bits of wood, because that butted end, if you tried to glue it, could simply unzip really easily. So that's why we use these sort of finger joints. Now, if you want to glue something, you know, the glue's got to sink in, so you've got to dry the wood before you glue it. So that's why the wood that you can see here is actually been spaced apart so that the air can flow around it during the kilning. It takes about a week in a kiln to dry down the wood. It's rather nice because all the heat to drive the kilns simply comes from burning the sawmill waste. And the other nice thing about drying out the wood is that actually you probably know that green wood is quite wet. As it dries down, it shrinks. But by drying it down in the kiln, it's basically all that shrinkage is happening in the factory before we make the glulam beam. So it's much easier to work, if we're building buildings, it's much easier to work with something which is going to be fairly stable. We can build in green oak, or any other green timber, but we're going to have to detail round all that shrinkage. So if we can make the shrinkage happen in the factory, in the kiln first, and then so we've got our long planks, we pass them through there, what's called a glue curtain. You can see there are actually 2 curtains. This one is the resin, and the second one is the hardener. So the idea is that the resin and the hardener, they mix on the surface of the wood. And then we simply stack up the planks, clamp them together overnight until the glue has cured. You can play with the curing time, but normally we work with about an 8-hour or so curing time. Now, what I've shown you there is a curved glulam beam, because obviously while the glue is still wet, it's really, really easy to pull those thin planks into a curved shape. Now, you can imagine if you try and bend them too much, they will simply snap. And roughly the limit is about, the minimum radius is something like 200 times the thickness that you can bend them to. So if you think that we normally have planks which are maybe 3 or 4 centimeters thick, so the minimum sort of radius is about 6 meters. If we want to go much thinner, Sorry, if we want to go to a much tighter radius, then we simply need to go for thinner laminates. So this was the timber wave that we did with Amanda Levitt now 5 years ago. You can see how she wanted these really tight curvatures. So what we did was we went for 6mm thick laminates. Now, nobody had actually tried to do a structure. This is furniture making. Nobody had done a structure before using such thin laminates. And you can do it, but of course there's a lot more sawing, there's a lot more planings, there's a lot more processing, cost in the processing, there's a lot more wastage of wood, there's a lot more gluing. So it simply gets more expensive. So that's why for a big structure, you know, the economics, the cost really matters. So trying to keep your laminates fairly thick, about 3 centimetres, 4 centimetres thick, limiting the minimum radius to 6 or 8 metres. Now, there's another advantage of laminating, and that is that if you take a tree, if you chop up the trunk into lots of planks, and if you simply strength test all those planks, if you put a weight in the middle until they snap, you will find that the strength varies by a factor of 3 or 4. Right, you know, wood's this natural material, very variable. The main reason it's quite so variable is that it has these awkward things called knots. Right, so I think you can imagine, you know, the knot is, I've told you that the trunk of a tree is like this bundle of drinking straws, but a knot, which is the remains of a branch, is kind of cutting through all those fibres. So you can imagine it a bit like a hole. So, you know, imagine if that hole is cutting right through your tension fibres, it's going to pull the strength right down. So that's why this piece here is probably only half the strength of that piece up there, which hasn't got a hole in a bad place. So that's why the strength of a piece of wood varies so much, and that's another advantage of laminating. Take the trunk, chop it up into pieces, glue them all randomly together. Those knots, those holes, don't go all the way through. And so we end up, we just know from testing, we end up with something stronger. And basically, the thinner you make your planks or your laminates, the stronger it becomes, because the impact of any one knot in any one layer becomes less and less. So glue lam is perhaps 30% stronger than the parent wood. And if you went to laminated veneer lumber, where your laminates are only 3mm thick, then that can be 50–60% stronger than the parent wood that you started with. So you can see what we're trying to do. You know, as engineers, we need a predictable material. The more predictable we can make the material, the better. Hence the great advantage of glue lam bins. You can make them essentially as big as you want, or as big as you can transport. So this was that's Jane. Jane did the engineering design for the aquatic centre for the London Olympics, and this was when we were looking at doing the roof in timber. So we went over to Austria to Vihag's factory, and they happened to have this there that day. So this is at 40 metres, this is about the longest glue lam beam I've seen. So by laminating, you can make bigger members, you can make stronger members, and as I say, they're much more stable because all that drying shrinkage has already happened. So the next question is, how do we join our timbers together? Now we can obviously, people are always saying the Sugaru Banse is very keen on using all timber connections, and all timber connections are fine. But you know, supposing that's a traditional mortise and tenon joint, you can put a wooden peg in that joint. In fact, some testing has been done here at Bath on the strength of those wooden pegs, and they're fine. But they will be limited by the strength of that wooden peg, because there's simply will come a point where it will snap. So the most modern timber connections are done in steel, and what you're looking at here is the very standard timber connection, which is steel plates flitched inside the wood. That's quite useful because the wood is the steel plate is hidden. It's also protected from the fire if you want fire resistance, and then those plates are fixed into the wood with, it could be bolts, or as in this case, just dowels, essentially steel rods. But even if we make the connection like that with steel dowels or steel bolts, the connection is still a lot weaker than connections into steel. And the reason is that essentially wood is this sort of brittle fibrous material. So this was a member at Munich University. We basically did a tension test on this member, and you can see how you've got the brittle fracture of the wood fibres. They can't take the sort of the stress concentration round the dowels. So the sort of load that you can carry on those steel connections, on those dowels in timber is much lower. On an M20 dowel, say, the load that you can take is much lower than the load that you could take on an M20 dowel joining to, or an M20 bolt joining two steel members together. And the other reason that timber connections are relatively weak is that, well, you can see here, there's a slot. So there's a slot that we've cut for one of those steel plates I was just showing you. But obviously, in cutting that slot, we have weakened the member. We've cut away 10% of the cross-section. So it is 10% weaker. So the slots, all the bolt holes weaken the timber, plus it can't take those stress concentrations. It fails in this brittle way. So the result is timber connections are relatively weak. And if you want a rough rule of thumb, if you've got a glulam beam, if you make a connection at the end of it, the connection can perhaps only carry about half the strength of the member. Maybe it's a bending connection, whether it's a tension connection, something like that. That's one thing. Now the other thing is that connections in wood are expensive. So this is perhaps an extreme example, but this is the roof that we did last year at Canary Wharf. It's over the new Crossrail station. And in this case, that was a moment connection that we were making between the members. But I think it's pretty obvious to you that all the money in this roof is in the connections. You've got these very simple timber members. They've grown with free solar energy. And then they're connected together with these fabricated steel connections, a lot of hand welding, hand assembly. And even though this is an extreme example, it is true of all timber structures that really a lot of the money is in the connections. So it's quite interesting because when we're, economics, keeping the cost of structures down is really important. If we want timber to compete with steel, to compete with concrete, we have to come up with competitive structures. So, in steel, the money is all in the tonnage of steel. So in steel, we're always talking about how can we minimize the tonnage? How can we minimize the weight of steel? But in timber, a lot of the money's in the connections. And remember, I've also told you that the connections actually govern the member sizes because the connections are the weak points. So in timber, a cheap timber structure is all about minimizing the number of connections, minimizing the complexity of the connections. So you might say, why do we do this roof like this? Well, first of all, here, this with Foster's and those connections became a very important part of the architecture. But in general, this had a relatively large budget compared to most timber structures. But generally, we need to work to a budget. So minimize the number of connections, and of course, the way we do that, as I've shown you before, is we go for really, really long members, and these are really not unusual. The members this size, we use some for the London Olympics. In the end, we did the tennis courts at Eton Manor. With a glulam roof, and those got 40-metre glulam beams, which were made over in Germany, shipped to the UK. It is very common. So whereas in steel, you'll always hear that in steel we should limit your steel members to 12 or 18 metres long to limit the transport costs. Obviously, there are higher transport costs if you go for really long members, but it's still cheaper doing that than to pay for all the extra connections. So just to give you an example of how that translates into how we engineer our timber structures. So this is on site at the moment. This will be the largest timber roof in the UK. That one, you're looking at one sort of panel there. That panel is about 15 by 15 metres with supports at the corners, but there are something like 30 or 40 of those 15 by 15 metre bays. So this is massive. This is Warwick University. This will be the new National Automotive and Innovation Centre. I think it's also got some of the Warwick engineering laboratories in it. Now, if you were doing that roof in steel, you can see it's basically a grillage. This is with Ted Cullinan. If that was a steel grillage, you would have a two-way spanning roof. You would have a moment connection at every single node. But I've told you connections in wood are expensive. Moment connections are particularly expensive. So in wood, you do it as a one-way spanning structure. So you can see those nice long glulam beams just simple pinned connections at the ends, and the timbers in the other direction are purely aesthetic, if you like. These sort of short infill pieces. So I know it's not as honest architecturally, but it's probably half the price of the alternative option. So that is essentially how we make timber compete with, and if we hadn't come up with this sort of solution, then we wouldn't have ended up with a timber roof. It would have ended up being a steel roof, probably. Now, sometimes it's, I've given you those rules, but sometimes it's okay to break the rules for one or two special structures. Particularly as Richard Harris is in the audience, I know you didn't work on this, but you work with lots of the engineers who worked on this. So this is the Mannheim grid shell. This is still the largest true timber shell which has ever been built. This was for the Mannheim Garden Festival in 1974. So this was Frei Otto at Stuttgart University, working with Ted Happold, who at that stage was running one of the building groups at Arup's in London. And of course, 1974 there was barely any computing power around. If you think it was only a couple of years after the Sydney Opera House. So Sydney was really the first building in the world to be designed with computers, so there weren't many computers around. So certainly not for an ordinary project like the Mannheim grid shell, so that really had to be designed by hand and with the help of these sort of hanging chain models. So obviously very much inspired, this is what Frei Otto was doing, very much inspired by Gaudi's work. And here you can see it under construction. So this is incredible. This is a roughly 40 metre span roof. Those timbers that you're looking at, they are simply 50 by 50 millimeters in cross-section. So, your overall structural depth there, you can see is something like 200 meters. So you've got a span to depth on this roof of something like 1 to 200. So you've got two of these timber laths in each direction. So they're loosely bolted together. You can see that bolt is in a slotted hole. So that was laid out flat on the ground as a grillage. And then very, very slowly it was lifted up into shape. So that's what you can see, these sort of scaffold towers that were used to help slowly lift it. This is during the lifting. Now, obviously, once it's in the final shape, you need to hold it in that shape. So the bolts are tightened. I think there was some, if I recall correctly, Richard, you'll know this better than me, I think there were some spring washers just to take up the residual shrinkage of the still slightly green timber. I think some shear blocks went in to join the two layers of timber together to try and make them work compositely. And you can see this sort of cross bracing went in to sort of start holding it in shape. Of course, it's a shell, so a shell needs a tension ring. So the shell was made over length, and then the edge of it was clamped between a pair of glulam beams. And so there's the finished result. This, as I say, most structures in any material, you're looking at a span to depth of something like 20. But if you can create a shell type structure, you can get up to more like 200 rather than 20. So incredibly efficient. Like an egg, really. Now, the reason to show you that, the 42-year-old project, is that was very much the part of the inspiration for the Met's Pompidou roof. So this was now back in, 2003, this was competition stage for the Met's Pompidou. There's Sugar Ruban's briefcase, this is at our meeting room in London, and this is the sort of Chinese-Japanese hat, which was his other inspiration for the roof, which he claims he found at in a Parisian market just next door to the Pompidou Centre in Paris. So now, I think the reason that Sugaru won the competition, he was really clever because he based the entire roof on the hexagon. So the hexagon is I don't know anyone in the audience is French, but the hexagon is the nickname that the French use for the French mainland. You can see why, because the French mainland is perfectly hexagonal. You have to use a bit of imagination. That's why I have to check if there's anybody French in the audience. But there won't be, because France has fantastic engineering schools, so I'm sure they'll stay in France. But you can see how the whole roof is hexagonal, and of course the hat was woven out of this hexagonal weave. Now the other reason, so this was felt to be a building made for France. The other reason that Sugaroo won that competition was that this was felt to be a building which was made for Metz. So what I've not told you is these are the 3 art galleries, basically concrete tubes. I should say concrete, nasty, unsustainable material. But anyway, these are the concrete tubes for the galleries, and there's a big window at the end of each gallery, and that window gives you a view out of specific points of Metz. I'll show you one of the views later on. So this was felt to be a building which was not only made for France, but was specifically made for Metz. Now, what Sugaroo particularly liked was the way that the hat was woven. So the top image there you can see is the hat. The middle image, if you go and visit the Metz Pompidou, you can see that is Sugaroo's first model, attempting to basically weave timbers to copy the hat. And at the bottom, this was an early Arup sketch where we were saying to Sugaroo, look, actually, if you've got big timbers, you just can't weave them, because they're too stiff, but why don't we layer them up? And that will give the impression of a woven structure. Now, I love this. The first time I was giving a talk on the Metz Pompidou, I was on an aeroplane. I forget where the talk. Oh, that's right. I was going to the States, and I opened the newspaper, and there was a big 2-page article on Metz, because it had just opened, and there was this lovely quote from Sugaroo, which said, "The design might look quite complicated, but it's really very simple." I'll let you decide if you think this was a simple thing to engineer. I'll also let you decide if you think it was one of our more profitable projects at Arups or not. I won't tell you how much money we lost on it, but hey, it was great fun. You know, the point is, you compare this with Mannheim, that perfect sort of Metz is not a shell. Because a shell, first of all, needs two-way curvature, right? And this is, as you'll see later on, the roof is supported on, there are 6 columns around the edge, and there's a big lift shaft tower in the middle. So that between that tower in the middle and the edge, this is actually pretty much singly curved rather than doubly curved. And the other thing is that, you know, a shell needs a tension ring, and this whole roof was lifted up off the ground on these 6 columns, and Sugaroo quite rightly was saying, you know, we don't want a big tension ring in steel or timber around the roof because it's really going to affect the aesthetics. So this is not a shell, this is a bending structure, so we're not at span to depth of 1 to 200, we're back to span to depth of about 1 to 20, and we've got much bigger members. These are something like, again, in the end, we had 2 layers, just like the 2 layers on Mannheim, but now instead of pieces which are 5 by 5 centimetres in cross-section, this is more like 40 centimetres by 15 centimetres, so much bigger pieces. You can see how, to fit the geometry, everything has to be doubly curved and twisted, and you can understand why these members could not be curved on site in the way of Mannheim to the final shape. These had to be actually fabricated to the right curvature in the factory. Now, I showed you how you make a singly curved glulam beam. Anyone want to suggest how you might fabricate a doubly curved twisted glulam beam like this? I keep asking this question, and I have to say, nobody has yet managed to answer it. But I still hope that one day somebody will. The clue is how you make a singly curved glulam beam. You just kind of have to take that a step further. No, I think everyone's too shy. So you take. What you do is you make some singly curved glulam beams, but can you see they're really, really thin? And then because they're so thin, you can actually bend them out of plane and you can twist them out of plane. And then you can glue them back together again. So essentially, you've got a member which is laminated in 2 directions. This is not Metz. This is a bridge in Holland, but it gives you the idea. So if you do go to Metz, it's only an hour from Paris on the train. But you can see that I've just drawn on these red lines, but showing how these very tightly curved columns have actually been laminated out of these tiny little rods of timber. Each one's only about 2 by 2 centimetres or so in cross-section. Now, I think you can realise that whereas making a singly curved glulam beam is pretty cheap, Making a doubly curved member like that, and particularly where every single member is made to a different geometry, different curvature, is just really, really expensive. So, I mean, the message I'm always giving to our engineers back in Arups, you know, when you're scheming something, is make sure everything is singly curved. In fact, we're doing a job with Sugar Ban at the moment in Singapore. In Singapore, the fees for building projects are really low. So I've said to Sugaroo, look, we've got to go for, if it's Singapore, we've got to go for singly curved members. But anyway, here it was going to be doubly curved. This is fine because this was being paid for by the French government, so they had loads of money. What's interesting is that the winning contractor or the winning fabricator realised that rather than making doubly curved twisted members everywhere, which was going to be really expensive, that actually a lot of them they could simply machine out of straight glue lambs. Right, a straight glue lamb, like on the left, you can buy that really cheaply, about £400 a cubic metre. The price is not, in fact, the price has effectively fallen by 30% in the last 15 years. So really, really cheap. We've got a big oversupply in Europe. And there you can see the CNC machine starting to machine that glue lamb down into these tiny little members. So, you know, obviously there's a huge amount of machining time, there's a huge amount of wastage, but it's still cheaper to do that than to make a doubly curved twisted glue lamb member. Now, there's a disadvantage in doing that. Anybody want to, you know, I told you wood's fibrous. Anybody want to suggest what the disadvantage might be? Yeah?
Cut out the straight.
Yeah, exactly. So, you know, if you make a nice doubly curved twisted, you know, properly two-way laminated beam, all the wood fibres are following the curvature. But if you do this, all the wood fibres are straight. And so now all the fibres are running out the side of this. And remember I told you that you know, that bundle of drinking straws are 5 or 10 times weaker perpendicular to the grain than parallel. So we could really only do that where the members were relatively straight up in the body of the roof. So and what we did was we said we can only do that where the slope of the fibres is going to be up to about 1 in 10. And where the slope was going to be more than that, then we couldn't do this. We had to go for proper two-way lamination. So there you can sort of see the finished roof. So basically it is this sense of, so you've got, you know, an upper layer, a lower layer, joined by shear blocks. So essentially what we're making is we're making I-beams. So what we've got is we've got I-beams which are intersecting in kind of 3 directions. That is the connection between the layers. Sugaroo wanted as much as possible to be done in wood. So we have gone essentially here for a big wooden peg. That's a wooden peg made of a beech laminated veneer lumber. So in fact now that beech LVL is now commercialised. It's something called Pollmeyer Baubucher. You can go out and buy it, but it wasn't very common 10 years ago. So a big wooden peg joining the layers, and here's the connection at the ends of essentially these glue lamb beams. There's the sort of standard connection I was talking about, these sort of flitched in steel plates held in with dowels. I said there were 6 supporting columns. We really called them funnels, and you can see how those were also sort of inspired by the traditional hat. Now, if you look at the base of that funnel, you can see how we've used a different timber. So, any thoughts about why we might use a different timber for the base of the funnel? What's the risk at the base of those columns? Water, yeah. So we've gone for larch, which has got some natural toxins in it. Just to give us a little bit more, I mean, most of the water will, to be fair, will it's slightly covered. Most of the water will sort of simply run off, but it gives a little bit more durability to protection against that rotting. And then up in the body of the roof, we've just used standard spruce, which is our sort of cheapest timber in Europe. So there is the lift shaft in the middle of the building. So that's what supports the middle of the roof that I was telling you about. And you can see these 1, 2, 3 essentially concrete tubes, which are the galleries. That's the view. So I said, you know, Sugaroo won the competition because he really designed this building for for Metz. So there is the view out of the end of that gallery of the old cathedral. Really, I mean, it's right. It is, they wanted a building to put Metz on the map, and which, and I think he really did an amazing job. The one thing I think, if I want to come up with one criticism of the building, it's that it's designed for a Mediterranean climate. It is not designed for what is one of the coldest places in France. So all the art is inside these concrete tubes. The only public space is down here. You can see all those sort of radiant heaters around the side. But this roof has no insulation. That's kind of important because, I'll show you the nighttime image in a minute, and you could see the structure shining through the membrane at night. But a roof with no insulation, so you need all this heat in the winter for these public spaces. But also, of course, in the winter, all those people are kind of breathing. All that warm, moist air is rising, and we were really scared that warm, moist air was going to condense on the cold timbers. Condense on the cold timbers, they're going to get wet, they're going to rot, and that's not good news. What we've done, the walls, we actually, believe it or not, this was a fairly low budget project, so we had to come up with a cheap solution. The walls were actually stopped 1 metre below the roof, so the walls cantilever from the ground level, the walls do not support the roof. And that means that we can get an airflow underneath just to stop that, to evaporate all that condensation, stop the wood rotting. So here we are during construction. So you can see all these doubly curved twisted members prefabricated in the factory with the shear blocks ready on them. There is now the second layer's gone on, and then the sheets of membrane which are fixed parallel to the upper layer of timbers, and that's our sort of team visit. There you can see really you get a sense for the scale of the members. That's Sophie in the background who did most of the work on this. The Peter Ross, there, my predecessor, who Richard Harris knows. Of course, because this was in France, all the meetings had to be held in French, despite the fact that our engineering team was in London and the fabricators spoke German. But the meetings had to be held in French, and so Sophie did a fantastic job. Having done stuff in French, she would then translate it all into English for the Arup engineers, and then she would translate it all into German for the fabricators. By the end of that meeting I went to, she was completely sweating. It was unbelievable. But anyway, the client was happy because the client only spoke French and they understood what was going on. The other great thing if you're having a meeting on a French building site is brilliant. Come lunchtime, everybody stops. You get a 4-course meal in front of you with a bottle of wine. You will never see a bottle of wine on a British building site. That's a finished building. I think really this building is a piece of modern art in its own right. I think people go as much to see the building as they do to see the art. In the first month, they got more visitors than they were expecting in their whole first year. That's the view at night I was telling you about. There is a fantastic French restaurant inside the building. So I popped out just before the main course and I took that photograph, and then I popped out just before pudding and I took that photo there. And I think, the sense in which I said, wood, you've got to play to the strengths of the material. Wood is incredibly easy to machine to these complex geometries. And I think, as an architect, if you want to create a very unique structure, wood is the easiest material to do it in because it is so easy to machine. It's not like steel where you're stuck with standard rolled sections that you go and buy. You can really make something quite unique. So that's very much in glulam. Now, I wanted to finish on something in CLT, because CLT, as you know, this is this new exciting material. As I say, it's this clever way of making massive panels from small planks of wood. And remember, wood's fibrous, it's only got strength in one direction, so what you have to do is you have to cross-laminate those wood fibres. So in each layer, the fibres are running perpendicular to the ones in the next layer. What you've made is, you've made a panel which, okay, it's probably only got about half the strength of a reinforced concrete panel, but it's got only a quarter of the weight. And of course, it can be machined to really high tolerances. So if you want to prefabricate a building off-site, and CLT is just a completely ideal material to do it in. And we were talking with Wen-Shao before how Legal & General have now, actually an insurance company, have now invested in a big factory in the UK to make modular houses out of CLT. So if you're going to make stuff off-site and transport it to site, having a accurately machined lightweight material is really the obvious stuff to use. So that's the idea of the Smile. So this is the Smile during construction. Anybody get down to London to see it? Oh no, okay. I'm sorry, it was only there for 3 weeks. That was all we had planning permission for. So, but we've got lots of photos of it. But it is like a giant piece of flat pack furniture. It's just made out of 12 of almost the largest CLT panels which have ever been made. The whole thing went up in about 5 days. It really shows I think it really showed the public the potential of CLT for prefabrication. Now, I've said that all the costs in timber are in the connections. So what's the cheapest way to join CLT? Well, the cheapest way is to use these screws. These modern screws, really high strength steel. You can put one in about 30 seconds with just an ordinary electric screwdriver. And yet each one of those screws can carry something like the weight of a car. Right, so that these screws are really incredible, and we had about 7,000 of those in the Smile to hold it together. 7,000, but still the whole thing went up in 4 or 5 days. Now, CLT is normally made out of spruce. So spruce, what you've got on the right, is what we generally know as a Christmas tree. The point of showing you that photo is that obviously Christmas trees have millions and millions of little branches. So the millions of little branches means that when you cut that up into planks, you end up with millions of knots. So spruce CLT always has lots of knots in it. If you look at, we've got more forest in Europe and North America than we know what to do with. We simply are not chopping the trees down fast enough. The forests are getting bigger and bigger. So I know there is a problem in the rainforests, but certainly in Europe and North America, we've really got lots and lots of wood fibre. About a third of those forests are hardwood, barely used actually at all. So we have this huge potential resource that we're not using. So about 10 years ago, we started to experiment with some American hardwoods, and we looked at a wood called tulip wood. It was quite interesting. It grew, those trees reached maturity in something like 40 years. Right, so this is most of our spruce coming out of Scandinavia. You're looking about something like 100 years to maturity, so 40 years to maturity on the tulip. Don't believe people who tell you that hardwoods grow slowly. I mean, yes, hardwoods in the tropical rainforests grow pretty slowly, but don't assume that applies to all hardwoods. But what was really interesting about the tulip wood, this is a graph of strength against density, and what we found was that although it's only got roughly the density of softwood, roughly only the density of spruce, its strength is much closer to oak. So we've got something really strong, but that low density matters, because if we're going to put in those self-tapping screws, obviously you can't put them into something which is as dense as oak. You need a relatively low density wood. So using the tulip, this is why we picked, it was now 3.5, 4 years ago, when I decided that tulip wood was, if we were going to use hardwood for CLT, tulip wood was the obvious wood to use, because it had the strength, had the nice appearance, but it wasn't too dense, so we could machine it fairly cheaply, we could make the connections fairly cheaply. And there we are, you see, so your spruce CLT is full of knots, whereas the one below, which is that's the tulip wood, sorry, it's not a great photo, but that's the tulip wood from the Smile, and you can see to look at, it's got very few knots, it's got the colour variation as you get in hardwoods between the dark harsh and the light sapwood, and I think really for exposed CLT, I think is a really interesting option. So there's the Smile. Now this wasn't just an experimental structure, right? We designed this to have 60 people standing at one end. I mean, we said we counted people going in, and we said maximum of 60 people at one time. But of course, you don't know where they'll go, and they might all choose to go to one end. So we designed 60 people at the end of the cantilever. Now that's a lot. That is a bit like the wind load on a 5-story building. Right, so you can imagine this actually like the core, the vertical stability core of a 5-story building, but I can tell you that nobody has attempted to stabilize a 5-story building with a wooden core, which is quite as small as the Smile. So this was, genuinely, this is the most ambitious CLT structure which has been built. Quite a lot of late nights, I can tell you. The first thing was, of course, if 60 people are going to run to one end, how do we stop the entire thing rocking? Now, lots of people said, well, why does it rock? It'd be really fun if it rocks. Well, it would be really fun if you're inside. So what we did, you can just about see here. We made this wooden box for a foundation. This was only a temporary structure, so the wood's not going to rot in a month or so in the ground. So we made this wooden box, and we counterweighted that wooden box with about 20 tons of steel weights to try and sort of stop that rocking happening. So there are sort of the steel counterweights. So here's the box before it was sort of dropped into the hole in the ground. Now the next thing is that, of course, under the weight of those 60 people, the whole end of the cantilever could simply snap off. Now, the story here is that when it was Alison Brooks with the architects on this, and when Alison first drew the Smile, and we thought, great, it's a really strong engineering shape. We did some rough engineering. We assumed all the stresses would be in the walls. We did some rough bending stress calculations on the CLT at mid-span, and it was, it really wasn't working very hard at all. Then Alison came along and pointed out that there would need to be a door. And this, I think, explains the difference between an architect and an engineer. This is a true story. Now, obviously, if you've got that big hole just where the bending stresses are higher, so obviously there's tension over the top of the door and there's compression underneath the door. So that was what governed the door's 2.1 meters high. Basically, this was working at about 90% stress over the door, so that's what governed what the overall height of the Smile was, to give enough tension strength over the door. And then we had to find a way of getting the compressions underneath the door. So basically, all that compression which is in the bottom of the wall, we've got to get that into the floor. So what we did was we used lots more of these diagonal screws, basically to stop the wall sliding against the floor. Now, the biggest engineering challenge of all was actually how do you stop that tube lozenging? So if you imagine what we created, it's like a toothpaste box, but it's a toothpaste box without the ends. So that box can just lozenge really, really easily. We were really struggling on this, and I will tell you there was a point at which this was actually now 1 o'clock in the morning, stuck in a hotel in Edinburgh because the city airport in London was closed due to bad weather. We had actually a meeting with Alison and the fabricator and the client the next morning at 10:30 in London, and this is 1 o'clock in the morning, and we're like, we just can't make this work, and we were really on the point of putting in steel cross braces every few meters down the tube. And we're like, Alison's really not going to like this. So what we then came up with was, and it's amazing how well the brain works at 1 o'clock in the morning. We were in a pub, but we didn't drink any beer. So what we said was, well, why don't we make it into a portal? So why don't we rigidly connect the roof to the walls? Now, it's like if you want to join two bits of plywood together, it's very hard to join together, so you need a batten or something at the connection point so that you can join them together. So that's what we did. You can see we put up on the roof, we put a pair of glulam beams. And so now we can take the wall, we can have a couple of screws that fix the wall into the glulam beam, and a couple of screws that fix the roof into the glulam beam. To make that stiff moment connection. And when I say a couple of screws, I mean we've got screws at 5 centimetre centres. But what's nice is that those screws became part of the architecture, and actually I think they enhanced the structure. So what we did was we CNC machined the start of those screw holes in the factory, so that they were very accurately positioned. So it became like this really neat row of stitching along the edge of the CLT. That's Sonia, Alison's colleague, who she worked several complete nights on the projects. That's my colleague Ishan. There was, I think twice I kept her in the office till 3:30 in the morning. So they're quite, these temporary structures where you have a really tight program, they're quite challenging, but they're really good fun. Alison's team was a real joy to work with. And now this is inside, so everything on this has a reason. So the floor, which way is the floor laminated? If you look at Alison's early renderings, the laminations in the floor are running up the slope, but of course you'll know that the floor has to span across between the walls, and so actually that's the direction of the laminations. And actually in the end that worked really well, because I was worried about people slipping on the slope, so I said, look, we've got to have some strips of wood running across to stop people slipping, and so those slips of wood you can just see here, those are nicely aligned with the outer fibres of the CLT. And there's that very clean view inside. You can see how having cross bracing would have really kind of ruined that internal shot. You can also see there basically the wall came in 3 pieces, central piece, 2 end pieces. Those end pieces to stop them snapping off. So again, you needed a tension connection at the top between the 2 bits of CLT. The CLT was only 4 inches, 10 centimetres thick, so we couldn't have a hinge connection, so we had to have this steel splice plate on the surface, which some people didn't like, but I think it was fine. Now, one thing, I think it was early July. I was actually on holiday. The fabrication was due to start 2 weeks later. 3 weeks later, Alison rang me up on the mobile and said, look, we've got to change the foundation detail. And she'd suddenly realised that the foundation that we'd agreed just wasn't going to look very good. What she wanted was that the smile shape would be very, very expressed, and that the foundation would be set backwards so you wouldn't really read it so much, that foundation box that I showed you before. And so literally this was some very late nights on this, but I could see that Alison was right, that we needed to come up with a different solution. And so what we can see we've done is we've actually we've made the floor thicker in the middle. We've extended the floor out sideways so the floor can cantilever beyond the edge of the box, the foundation box, and now the wall can come and sit on that cantilevering floor. And I think what's rather nice is that then you could see the edge of the piece of CLT. So there's this sense in which in a timber structure you can really see how everything works, how everything goes together. So as I say, I think just to finish, wood's this incredibly versatile material, and because it can be both structure and finishes at the same time. So that's great, but of course what that means is that everything is visible, and that's why I think it demands this. I mean, architects and engineers always need to collaborate, but I think in wood you need to collaborate much, much more than any other material. But what it does mean is that it's just a much more exciting process. I mean, I will gladly say that this project is the most exciting project I've worked on, and that is because of that incredibly close relationship which we developed with Alison's team. Yes, you do work really long hours, but actually you're all pulling in the same direction. We on this foundation detail, I could see that Alison was right, that we really needed to work hard to come up with a different solution. But equally, a week after that, we discovered that we were short of tulip wood, and we needed to save some material. And I said to Alison, look, at we've at that stage, quite a late stage actually, both the floor and the roof were actually made of, the whole thing was made in a different way. The whole thing was made out of about 50 planks of CLT. The floor and the roof were actually faceted. The walls were actually curved on plan. I basically said, look, the only way we can afford this structure, the only way we can actually work within the volume of wood we've got, is to build it like this. I said we've got to make it out of just 12 panels. Instead of curving the walls, we're going to curve the floor. Instead of making the wall out of 5 pieces, which Alison wanted so that all the boards could be horizontal, I said, look, we can only afford to make it out of 3 pieces. That saves material, that saves money, less connections. But what that means is that the boards here are no longer all horizontal. It means the boards in these edge panels are actually sloping. And that was the point at which Alison knew that she needed to compromise. So on these timber structures, it's really important that your job, as much as to come up with the solution, is also to know as engineer or architect where you need to compromise and where you need to hold on to things. So I hope that will inspire you to go and design some timber structures. So thank you very much.
Okay, question? Right.
Good question. The theory was that it would all run to the middle, and on the back there's a little drainage spout, a bit like a gargoyle. The reality was that the guys who built it were not actually fantastic, and they built the whole thing slightly wonky. So the water all pooled on the front edge, and then the client couldn't afford a proper waterproofing membrane on the roof. So 2 hours before the big press opening, we had water pouring inside. But anyway, that was the theory. We then basically, I have to say, I had no involvement in the waterproofing, other than I've been saying continually we need a proper rubbery waterproofing membrane on the roof. But we then basically, we were really lucky because it didn't then rain that much for the rest of the 4 weeks.
Any other question?
You were saying that making connections in metal was quite expensive, but is it possible to cut costs by making dowel connections out of timber where they're necessarily not as huge stresses for each connection?
Well, yes, I mean, that's what I'm saying. So, yes, and I showed you the traditional mortars and tenon joints. So, yes. But the point is those original mortars and tenon joints are not that strong. So, as you guys have demonstrated, you can take some tension on them, but it's relatively limited. So, so if you look at, say, Sugar Band's Tamedia office building in Zurich, where he wanted to do everything completely in wood. I mean, he's achieved it, but at the connection points, suddenly the members grow massively to kind of make the connection work. So you can, and there he's turned it, is great, he's made it part of the architecture. But what we are, say on that Warwick roof, I mean, what we are starting to see more is, on that we've managed just to have screws and no other fabricated metalwork. So that's probably as cheap as you can get in terms of modern connections. Yep.
How do the metal joints cope with the expansion and the contraction of the wood due to the weather or the temperature?
The thermal expansion and contract. Sorry, say again. Yeah. Well, thermally, so thermally, wood is really stable. First of all. So the actual issue is that wood is across the grain, it will shrink and swell quite a lot. So actually, during construction, most CLT or glulam it's manufactured at about 12% moisture content. It will generally go up to about 15 or 16% moisture content during construction, and consistent with that, your glulam beam will swell by about 1% across the grain. So if you've got a 1 metre deep glulam beam, it won't get any longer, but it will get about 10 millimetres deeper. And then after you switch on the heating in the finished building, it's going to dry down by about 4% moisture content, or about 1% overall. So it's the cross-grain drying shrinkage that you need to deal with. And that is why if you had a 1 metre deep glulam beam, you wouldn't put a 1 metre deep plate in the middle of it, bolted to it, because you can imagine as the wood tries to dry and shrink, the plate is going to restrain its shrinkage, and the wood will simply split because it can't deal with it. So that is the trick, is basically everything happens across the grain, and what you do is you keep your steel plates quite small. So if you look at a steel moment connection, that on a big member, the way you'll do it is you'll have a plate at the top for the compression or tension, and a plate at the bottom for the compression, and you'll have a plate in the middle to carry the shear, but the three plates won't be joined to each other, so that the wood can easily sort of move, shrink, swell across the grain.
What was the main reason behind building this structure?
This one. This was essentially, it was built for the London Design Festival. So there is a tradition of building experimental structures for the London Design Festival, but essentially this was essentially paid for mainly by the American government as a marketing for their American hardwoods. It wasn't completely paid for by the American government, because a lot of our time, basically there was 1,200 man-hours of engineering went into this. and probably about 400 man-hours of architecture. So both of those were way above what even the American government could afford. So there was a lot of Arup time went into this too. It was great. I mean, we learned a huge amount from it. I mean, it genuinely is the most complex CRT structure that's been built. And so there were lots of really interesting engineering lessons that come out of it.
Okay, yeah, then thanks very much for Andrew again. Right, okay, then let's close today's talk. Okay.
Yeah, sure. Yes. Oh, really? Okay, right. Have you done any testing on that? Well, so yeah, I mean, usually group charges, of course, they're completely autonomous in terms of working out what it is. So in terms of Mannheim, there's the original paper in the structural engineering is working on it. So you can get that out to the eye structure. But there's this like a 20-page paper in terms of how the engineering design it, and that's what we I mean, in terms of, I don't know much else that's been written about bridge shells or other sorts of shells. I mean, we wrote a paper in the structural engineering